Hi folks, Mr. Ackerman here. Thanks for watching. We are now on lesson 2 of Unit 2. We're starting to get into some applications of Newton's second law, but as they relate to the more challenging grade 12 questions, to distinguish them from the more simple grade 11 style questions. So just to show you where we're at in the homework schedule, we are in lesson 2 as I mentioned. We're in section 2.3 of the textbook, applying Newton's laws. As usual, make sure you take some notes in there, watch the sample problems. And also there's one part that you have to go to your course pack for. That's this one, motion on inclined planes. It's in your course pack. Today we'll deal with case number 1, no friction. Some questions for you to try in class here, as well as some for after class. And of course, learning goals and success criteria down here. Pause the video, have a look at them. And in the interest of saving time, let's get started. Just so you know, I'm going to teach this part of the unit by showing you a whole bunch of problems that deal with the following ideas. Pulleys, which are new to you grade 12s, inclined planes, which I mentioned, that's what's in the course pack here, and special instances where the normal force and gravity are not equal to one another. Two of these you didn't encounter in grade 11, pulleys and inclined planes, and one of them very, very rarely. If you remember in grade 11, the normal force and gravity always have the same magnitude, or almost always. Here we're going to show where that's not the case. So keep your ears and eyes open and let's get started. First type of question that you're going to deal with that is new to grade 12 is pulleys. Pulleys are interesting machines. They help redirect force, and they also can do so without any friction in an ideal world. And if you configure a pulley system in a clever way, you can actually use very little input force to generate a whole lot of output force. In fact, I'm going to show you a demo in class where with just a simple pulley setup, I can double the force I'm able to exert. And in fact, using the idea, you could even triple or quadruple or do whatever you want to the force that gets output. In that way, I could even rig a pulley system that would lift our entire rugby team, for example. Something I could not do single-handedly. But just to get back to the question at hand, let's start with a simple example of pulleys and look at how these things work. So I'm looking at sample problem 3. This is in our physics textbook, Physics 12 by Nelson. The problem is done for you by them, but I'd like to dive into it and take a close look and show you a little shortcut way that you can solve this. So the question has a loonie on one side and a dime on the other. The mass of both of these are given. And as I'm sure you can imagine, if you were to rig up this pulley system and let it go, the loonie would go down because it's the heavier one, and the dime would go up. So something that your book does is they designate up as positive on the right side, but down as positive on the left side. We have to do that because that's the direction of motion of the system. This is really a one-dimensional question, and we want to basically think in terms of the forward direction being down on one side, up on another. So now, let's analyze the forces that are acting. If we start off with one that's quite often going to be there, gravity, the dime is experiencing some gravity downwards, of course, but so is the loonie. And as you think critically through these problems, make sure you draw those force vectors to represent the fact that sometimes one force might be longer than the other, showing that there is more force. So this is Fg on the dime, and this, of course, is Fg on the loonie. And these are equal to just mass times 9.8. So this one here is mass of dime times 9.8. And the other force, of course, there's a string here, so there's tension in the string. I'll put that in a different color. We have tension. The tension always points along the string. So in this case, it would be up. This one's going to be Ft. But the question I have for you is, what will we write for the tension on the other side? Well, I'm going to show you a demonstration in class, which is actually hopefully going to convince you that the tension on both sides, believe it or not, is the same. One way to remember this is that it's the same string, and the pulley is frictionless. Therefore, the tension magnitude is the same. Although the tension direction is different, the string is holding up both of these objects as gravity pulls down. So the tension can go both ways in the string at the same time, just acting on different objects. So that's something that you're going to have to wrap your head around. And the demo, as I mentioned, I'm going to show you in class, that will convince you that the tension is the same in all parts of the string. So keep an eye out for that. Now, if we look at what's going on here, you can follow along with the way your book solves it, but I want to show you a little shortcut. So here's the shortcut method, which is going to allow you to solve for acceleration. So let's write solve for the acceleration, and this is the shortcut method. So you might want to note that, because you don't have to use this method. You can do it the way the book does. But the idea here is simple. If you look at the whole system, in other words, look at this as one object. What direction is it going? It's going down on the left side. When we look at it as a whole system, we realize it's the battle here between the two gravity forces that's leading to the motion. The reason the loonie goes down and the dime goes up is that the loonie is heavier. So when we're talking about the system and we write the acceleration formula, which is F net equals ma, or F net equals ma, or a equals F net over m, we have to realize that in the positive direction on the left, there's the force of gravity. So that's positive mg, and that's mass of the loonie times gravity. But on the other side, fighting this, therefore minus, is the force of gravity of the dime. So mass of dime times g. Loonie pulling in the positive direction, dime's gravity pulling in the negative. Now what about these tension forces? Well, as I tried to convince you earlier, and I will in class with a demo, these two tension forces are equal. And they're also in opposite directions. Now, they are acting on different objects. However, if we do what we set out to do, which is look at the whole system as one, then these are really what we call internal forces going in opposite directions and being equal, and therefore they cancel. So when we go and calculate F net, the good news is you don't have to worry about the tension. You just have to divide by the mass. What mass would you use? Well, it's going to be the mass of the dime plus the mass of the loonie, because once again, it's the whole system that we're looking at as one. Now, I believe the question gives you all of these numbers. Here's the mass of the loonie, here's the mass of the dime. You know what 9.8 is, so you can plug in all of these numbers. And I'm not going to waste your time doing this. It's done in the book and you can use your calculator, but this will get you a value for the acceleration, which should match up with what's in the textbook. Once again, this is a shortcut method that gets you the acceleration. We do it by looking at the whole system, where all we regard or look at is the external forces. So I'll write that down just to emphasize it. Internal forces, when we look at the whole system, cancel. And some of you I know maybe, I don't want you to confuse this with other situations where these forces don't cancel. The way to think about this is kind of like, imagine this. Your heart pumps blood downward toward your legs, let's say. And of course, if the heart pushes the blood down, the blood pushes the heart up. That's just Newton's third law, right? Well, let me ask you this. Does the beating of your heart and the forces that are exerted, does that ever accelerate you? Of course, the answer is no. These forces are internal to your body. Therefore, they act on the same object, you, and therefore they cancel. In much the same way, these forces, when viewed internally, cancel out. So keep that in mind. That's what we call the shortcut method. Of course, what you might notice is that when you do this method to get acceleration, what you don't get, and what they ask for, is the tension in the thread. So while the shortcut method gets us part A of the question, the acceleration, how do we get the tension? Now you have to look at one object at a time. The reason we have to look at just one object only if we want to get the tension is because now we don't want the forces to cancel. So let's see, what would we do here? I will put a box in orange, let's say, around one of the objects. I'm going to look at the dime right here. There it is. And I'm just going to put a little arrow here to emphasize that I'm only looking at one object this time. So let's see what you get. If we write Newton's second law here, we'll have acceleration equals F net over m, once again. But this time we're only talking about the dime. So what do we have to do? Well, we write A equals, and we look for F net. What is F net? We've got tension in the positive direction, so I'm going to write positive Ft. We've got gravity on the dime in the negative direction. That's minus m dime times 9.8. Those are all the forces acting. And this time we're only dividing by the mass of the dime. Now, if you look at your answer from this part, part A, you already have this. So sub in the acceleration. The tension is what we're solving for. Once again, we know the mass of the dime and we know g, and we know that. So we're going to solve for the tension force rather. And again, your book does this and you can do this on your own. That way I can save time and get you through this a lot quicker. So there you go. This is how to solve a basic Pulley question. One idea that I neglected to mention in the beginning is the fact that the acceleration of the dime and the loonie must be the same. So let me put that in there, and let me see if you can think of why this must be true. Same for loonie and dime. Why is that the case? Think about it for a moment. Pause the video if you have to. The reason they're the same is that if they weren't the same, eventually the string would break. And I think we're assuming in this question that the string doesn't break. If you accelerate these two guys at a different rate, they're going to pull the string apart because they won't be moving together. Anytime objects are connected like this and there's no breakage, they accelerate together. Therefore, we can use this acceleration value in here when we look at just the dime. Okay? Let's go to something a little more challenging. I forget which page this is on, but it is in the homework, and it's question number 5. I'm sure you'll find it by looking through the textbook. Here we have a slightly different question. We have a vertical hanging mass like we did before, but we also have a mass on a table. But then again, there's that pulley. And they ask you to imagine that this time there's also friction right up here acting on block A. 5.7 newtons is the force of friction. And so what are you going to do now? They also give you the masses of the two objects. Well, first of all, you're going to analyze this and realize that this system can only go one way. B has got to go in the downward direction, and A has got to go to the right. So I'm going to designate these as positive. It would be highly unusual to see B going up, defying gravity, unless you pulled on A or something like that. Now, since this is the positive direction, what are we going to do? We're going to use the whole system method like we did before over m. But we're looking at the whole system, so let's look at what forces are acting. For example, there is gravity once again on B, and there's also gravity on A, for that matter. B is not the only object that has gravity. So let's write that in. This is FGA, and this is FGB. What else have we got? Well, there is tension in the rope, and that would be up for B. It would also be to the right for A, in much the same way that the tensions went opposite directions over here with the loonie and the dime. And these are the same tensions for reasons I discussed earlier, so they just get FT. You don't have to write A and B for those. What else have we got? We've also got friction for block A, but no friction for block B, so I'm just going to write FF. And of course, block A is sitting on a tabletop, so there's going to be a normal force acting on it as well. And I'm just going to somewhere here write in Fn. There we go. Couple of observations. We're going to assume that this block goes horizontally across the tabletop, and therefore we can safely write that the magnitude of the normal force and the magnitude of the force of gravity on A cancel. And therefore we can actually ignore them. In fact, the only forces that matter then are friction backwards, tension and tension, which again are going to cancel, and the gravity on B. So think about this. What is this? It's nothing but a tug of war between the gravity on B and the friction on A. So what's F net? The positive direction is down. That's positive Fg for block B. It's negative FF on block A. Divide by the total mass, because we're examining the total system. Force of gravity on B is mass of B times 9.8. The friction force is given. The total mass you can calculate. And at this point, let's see, do they give us MB? Yup, Do they give us MA? Yep. Do they give us MB? Yep. We know 9.8. Friction force is also given, so you're going to solve for A, the acceleration. Check that you get the right answer in the book. What do we do at this point? We've already solved the first question, what's the acceleration? Now we want the tension in the strings. Well, it's just like we did here. We now isolate one object. That way the tension force doesn't cancel out. So last time I drew a box around the one object. Which object should you draw? Probably the simpler of the two, and that in this case is the hanging object. So right over here we're going to do what? Well, we're going to write once again Newton's second law, A equals F net over m. The acceleration we're going to use from what we just discovered. I'm going to put that there. We're going to write in the forces here. I've got positive mass of object B times 9.8. I've got negative tension force going the opposite way. I'm going to divide that by the mass of B, and look at what we have. We know the acceleration from the first part, we know the mass, we know 9.8, we know the mass once again, and you're going to solve for Ft. And that's it. That's how we do Pulley questions. It's basically looking at them by saying the accelerations will be the same, the tension forces will be the same. We use the whole system method to get the acceleration, and then we isolate one object to get the tension. All right, let's move on. In grade 12, you're also going to deal with a new kind of system involving what are called inclined planes or ramps, or for those of you who are looking forward to the winter, ski hills and snowboard hills and all that sort of thing. So let's see how these work. This is probably fairly new to most of you. So first off, I want you to imagine an object whose mass is m sitting on an inclined plane. Now, what happens to this object? We all know that it rolls down the hill, right? Well, not always. Sometimes you can have an object on a hill that isn't moving. It's possible for you to maybe stand on a ski hill and arrange your skis in such a way that you don't slide down the hill, you know, when you just want to take a break. So those are possible situations, but they involve friction or some other force that you apply to hold yourself up. I'd like to ignore those for a minute. We're just going to do no friction at this time. In the next lesson, we're going to add friction. So what forces are acting? Well, let's start off with an obvious one. There is gravity, and gravity, as you know, acts straight down toward the center of Earth. So I'm going to write that in over here, and that, of course, would just be mg. There's also a normal force, and from thinking about what the word normal means, remember it means perpendicular, I hope you can see that the normal force is actually going up and to the left. It's on an angle. Remember, it's got to be normal or perpendicular to the surface. What other forces are acting? Remember, there's no friction. And so you might be wondering, well, I know that this object's going to roll down the hill. Isn't there some sort of force pointing down the hill? And you might be tempted to put that on. You might be tempted to say, is this an applied force? Is it a magical force? Is it a hill force? I don't know. What the heck could this be? Well, the good and bad news is there is no other force that's pulling down the hill. This is all just in your imagination. How can that be? That's the bad news. If you thought there was a force, now you're thinking, uh-oh, I don't understand any of this stuff. Well, let's solve that problem. Let's take a look at something. You guys are used to thinking of the following coordinate axes. You're used to thinking of the x and y direction being like this. Sorry, this is the y direction, and that's the x, right? Well, let me propose something that's going to help us understand this situation. Instead of thinking about x and y like this, since we know that the mass is going to move down the hill, how about we do this? How about we say, let x go down the hill. In other words, let's rotate our frame of reference around a little bit, our coordinate axes, that is, and that's going to make the y direction point up like this. Let's make this the y direction and this the x direction. So kind of flip this left to right and then rotate it a little bit so that now the movement direction is corresponding to the direction of the x-axis. This is the direction where the motion is going. This is why we might want to do this. It's going to make it easier to view the motion. So we're done with that coordinate system or frame of reference. We're going into a rotated or tilted frame of reference. Now what does this do? This allows me to do the following. I can now say that this direction here is the y direction, and this direction here is the x direction. Now, any inclined hill is inclined at some angle, theta, to the horizontal. Now let's see, this is theta. Gravity makes a vertical, so this is a right angle. That makes this angle in here 90 minus theta, and because this is a right angle, therefore this is also theta. If that didn't make any sense to you, and I'm sure most of you are going, huh? Pause the video and go back and listen to that explanation again. I'm going to move on to save time. Now that we agree that this angle here is theta, let's analyze gravity one more time. Gravity, you now see, has components in the vertical, the new vertical, and the horizontal, the new horizontal direction. Let me do these in a slightly different color. There we go. Gravity now has a component that is in the negative y direction, and we call this FGY, and it points down. And it's also got a component that points down the hill, which is the new horizontal direction. We call that FGX. The gravity force has components that go into the hill, the y direction, the new y direction, and down the hill, which is the direction that the mass is moving. Can you now see why the mass rolls down the hill? It's because a component of gravity is pulling down the hill. There's no applied force or magical force or hill force or whatever you want to call it. It's actually a part of gravity. And for that matter, if you think components in SOHCAHTOA, convince yourself, or calculate it better yet, that FGX is going to be mg times the sine of theta. So this is on the sine, the opposite side of theta, so we give it a sine theta. And FGY is equal to mg cos theta. SOHCAHTOA, folks. Here's a triangle for you, right in here. Do SOHCAHTOA on that and see that FGX, which is along this side, by the way, and FGY, which is along that side, and the right angle and the theta lead to these two components. Now, this pulls us down the hill. What does this one do? Well, if you look at it, FGY is opposing the normal force here, which I originally had in a sort of magenta color. So can you see that this is now the force that opposes Fn and actually supports the skier on the snow, if this is a snow-covered ski hill, as opposed to a non-snow-covered ski hill. That's not much fun. But anyway, M doesn't sink into the hill because something's holding it up against the y component of gravity. That something's the normal. So Fn is actually equal to mg cos theta. What is FGX doing? It's pulling us down the hill. It's causing the acceleration. In other words, look at what's going on here, guys. The only force in the x direction is FGX component. Therefore, we can write that FGX is the net force, and therefore mg sine theta equals ma. And guess what? The mass cancels, and you end up with A equals g sine theta as an equation for any object on an inclined plane when there's no friction. Does this equation look familiar to you? It should. There's the letter g, which we have to have if there's acceleration due to gravity. But think about the sine function for a moment. When the angle theta is very small, sine of theta is very small. Imagine a ski hill with a very shallow incline, the beginner hill. You don't accelerate very much. Low theta, small sine theta, g times a small number gives you a small acceleration. You don't accelerate at 9.8 when you go down the beginner hill, do you? On the other hand, the double black diamond hill, really steep, really challenging, large theta, very steep hill. Plug in a large theta value, the sine of that will also be larger. Multiply it by 9.8, you get a larger acceleration. Is it true that you accelerate more rapidly down a steep hill as a shallow hill? Of course. So this formula makes a lot of sense. If theta is 0, meaning there's no hill, it's flat, sine of 0 is 0, no acceleration. Yeah, standing on flat ground, no acceleration. And if the hill were vertical, 90 degrees, which you could imagine you just fall straight down like going over a cliff, put 90 in here. Sine of 90 is 1. 1 times g is g. A equals g. You would accelerate down at 9.8. This formula is really smart. So let's use it in a calculation. Question 7, I also forget the page. I apologize. It's in your homework schedule. I'm sure you'll find it. Has a skier going down a hill which is inclined at 12 degrees, and there's negligible, so we're going to read that as no friction. They ask you for the normal force on the skier and the skier's acceleration. Well, I don't want you guys to memorize these formulas for Fn up here and for Fg here. I'd like you to get used to drawing the free body diagram, because in some challenging instances, it'll really be important that you know how to do this. So let's put a skier here. Let's decide, okay, we know the skier is going down the hill, so we're going to use a new coordinate system where this is the positive x and this is the positive y. We're going to realize that the only two forces acting are gravity, which is straight down, Fg equal to mg, and also Fn, whoops, meant to use a straight line there. There we go. There's Fn. And if we want, we can imagine the coordinate axes sort of being superimposed like this, so we can see exactly what's happening. Theta is the angle of the incline, and again, that shows up. So we've got a component of gravity that is this way, that's called Fgy, and we've got a component of gravity that goes this way, which I'm just going to draw up here so that things don't get too messy, Fgx. And of course, doing SOHCAHTOA along with the mg side of this triangle, that would be, if we look at this triangle over here, you've got something like this. Basically what we're saying, just to reiterate, that's mg, this is theta, this is the right angle, this is Fg in the y direction, and this is Fg in the x direction. SOHCAHTOA gives you what we got back here. So in the end, I'll leave it to you to do all of these substitutions and writing, but we're going to get A equals g sine theta, which is simply 9.8 sine of 12 degrees. The sine of 12 degrees isn't very much, so when you multiply it by 9.8, you won't get a heck of a lot. I wouldn't expect a skier on a 12-degree slope to accelerate very much. Solve this on your own, please. Save me time by not having to punch into the calculator. And of course, Fn, which is equal to Fg in the y direction, which of course over here we see is mg cos theta. Well, now you need to know the mass. If you want to know the normal force, you do need to know the mass. 65 kilograms times 9.8 times the cos of 12 degrees. Again, plug that into your calculator to see what you get. One last point about these inclined planes before we move on. Does it bother you that in the acceleration formula there is no mention of mass? Dependent, there we go. Does it bother you that any skier, a little kid or you, accelerate down at the same rate? I hope it doesn't. Think about it for a minute. Do objects accelerate due to gravity when they are free falling with any dependence on mass? If there's no air resistance, no. They just accelerate at the same rate, light and heavy objects. Remember the hammer and the feather on the moon video, or the feather and the coin in an evacuated chamber video when we talked about drag forces. Well, why should it matter on a hill then? The fact that mass cancels out confirms that idea or builds upon that idea. All right, moving on. This question here, I'm not going to solve it for you. I'm just going to point out a few things. This combines pulleys and inclines. A couple of things to point out. There's no friction, so that keeps things simple. But can you combine what we just talked about with inclines over here with what we talked about involving pulleys on the previous two problems ago in order to solve this? They've already given you a pretty big hint. This mass goes down and this mass goes up. So can you combine your ideas of inclined planes that we just talked about, plus the idea that we learned here about pulleys and how one object goes one way, one goes the other way, tension forces that are internal? If you're comfortable with simple pulleys and you're now comfortable with inclined planes, try this. This will be a good challenge for you. And if you get stuck, there'll be time in class to have a look at that one. All right, I'm not going to solve this for you right now. We finish off with another new grade 12 idea. This is one where the normal force is not the same as gravity in terms of its magnitude. Now, if you think back to grade 11, you always had something like this. You had, someone or something that was on a horizontal surface, and you said, okay, Fg equals mg, whoopee, Fn points straight up. This is what they look like. And you wrote this, Fn equals Fg, Fn equals mg. I'm going home. I'm done. Well, in grade 11 simple questions, sure, that's the case. But a demonstration that I have done for you in class, or if I haven't done it yet, I will do it, involves the following. I'm going to, at some point, put a scale on a table. So let's put a scale there. And I'm going to place an object on the scale. There's the scale. It's got a little dial there that reads whatever. I'm going to place some object on top of it, and it's going to tell me what the mass is. And I'm going to think that scales read mass. But then I'm going to take my hand, and I'm going to push down. That's my hand, by the way, in case you're wondering. And I'm going to push down on the scale. And now you're going to see the mass, of course, increase. And then I'm going to lift up on the object, and you're going to see the mass decrease. And I'm going to say to you, is the mass really changing? And you're going to say, no, it's just that you're pushing on it. So I'm going to say to you, is it true that scales read mass? And you're going to say, well, obviously not. What do scales read? The only time a scale reads the true mass is when you don't touch the object, pushing up or down. In other words, when the normal is equal to gravity. The minute you change the normal force by pushing down or pulling up, you can't say this anymore. Well, that can happen in, for example, this question. Let's take a look. A boy pushes a lawnmower from rest, okay, and he's pushing it so it goes horizontally across the lawn. Just imagine someone mowing the lawn. However, pushes down on the handle. Now, how would this look if we were visualizing this? Remember, physics is about real things, so you should always try to visualize what a problem looks like. Here is my awful rendition of a lawnmower, but never mind. The important thing is someone is pushing a lawnmower. The lawnmower accelerates horizontally. We've all seen someone mowing the lawn. It tells you here the handle is inclined at an angle of 35.1 degrees above the horizontal. That's in here. Make sure you're good at drawing diagrams. Remember, good diagrams come from good thinking, which leads to good problem solving. What would this person be doing? Would he be pulling up? No, he'd be pushing down. We've all pushed a lawnmower before, or pushed something similar to a lawnmower, so we can envision this. In other words, there is a force directed down like this, and I'm going to call that the applied force. Now, of course, there's also other forces acting. For example, there will be gravity acting, and that's equal to mg for the lawnmower. There will be a normal force. We are on a surface. The surface is the ground. Oops, that wasn't very straight. Let's try that again. There's the normal. And the question also talks about friction. You find this out, I believe, a little bit later when they ask for the friction force. I don't know why they don't say it in the question up here. You kind of have to read a little bit to figure it out. But there is friction, and as we've mentioned on numerous occasions, friction acts opposite the direction of motion. So hopefully you can figure out that there's a friction force backward. So now my question to you is the following. If nothing is pushing completely forward in the direction that you know the lawnmower is going to go, what is responsible for the acceleration of the lawnmower? Think about this. Well, if you think about it for a moment, hopefully you'll begin to see that the force responsible is the applied force. First of all, you know that when you push a lawnmower, it goes forward, so it's got to be the applied force. But secondly, from a physics standpoint, can you see that the applied force here has a component which is forward and also a component that is downward? I hope you can see that. Oops. After all, the boy is pushing somewhat forward and somewhat down. If we take this force vector and think about it for a minute, here are the axes that we call x and y, and here is the force vector. That wasn't a very good force vector. There's the force vector. Now what's the angle here? The angle is said to be 35 degrees with the horizontal, so that goes in here. And this is FA. Can you now see that FA has two components? It's got FA cos 35.1 degrees, and it's got negative, because of downward, FA sine 35.1 degrees. This is a big help for this problem. I'll see if you can figure out how to use it. As you know, the bell just went, so I got to get to my next class. But just a few other things to help you. FG is down, so that's going to be 0 in the x direction, but negative mg in the y direction. What else have we got? We've got the normal force, nothing in the x direction, all of it going up in the y direction with an unknown amount. And then finally we have friction, which is all of it in the x direction going backwards, so negative F, sorry, I just realized I wrote FA, that should be FF, my apologies. All of it in the negative x direction, none of it in the y direction. And of course, all of these are supposed to add up to what we call F net, which has components in two directions. Now, what are these components? Think about it. The lawnmower is accelerating across the lawn, like I've seen people do on Saturday morning in my neighborhood. That's an x acceleration. Lawnmowers don't accelerate up into the air or sink down into the ground, so 0 down there, MA, everything in the x direction. Here you go, folks. Here's your gift. All of the forces have been written in components. You know that these four forces, line them up and make them add up to this, and see if you can solve for the normal force and the friction force for the lawnmower. All right, that's it for today. There's 3 problems for you to work on, more in class. And sorry for the long one, but there was a lot to cover. Talk to you later. Have a good day.